I'm Jingya Li. I'm going to talk about isogeometric analysis suitable coupling method for fluid structure interaction with our solid structure solver G+Smo coupled via preCICE. I think maybe some of you only understand some part of this title, but don't worry, I'll give short introduction for every part. So I'll start with our application, which is this very flexible floating structure. I mean, in the Netherlands, we have a very serious land shortage. So we try to build this kind of solar farm on top of the sea. So this is a traditional solar farm. So you have this kind of platform, and you have something like the beam structure on top of it. And this is our application. We have this very flexible membrane-like platform. So in theory, what's the difference between them? So for the first one, you're solving this classical hydroelastic equation. And for our problem, you're solving this Foppelman-Karman equation. So the difference is here. Like you have this second order derivative to your displacement. That means if you want to have this memory effect, you need to achieve this C1 continuity on your computational domain. Also our application is very large scale. So it's equal to 5 times of the football field. And we also want to achieve this C1 continuity. But I mean, it's a very complicated task. So we decide to do this fluid structure interaction simulation with preCICE. So far, we have our structure solver, G+Smo. And we want to couple this structure solver through preCICE with openFOAM, WaterLily, and Noodles. Well, don't feel excluded from this if your library are not there. It's because we only tested our code on these 3 libraries. It's not like we are not going to do this in the future. Yes, and maybe some of you may think, why do you not develop your own fluid solver? It's like my supervisor, Hugo Verhulst, he spent his entire 4 year and he only achieved this thin shell structure library. Then one day he said, yeah, if you spend your entire 4 year to develop a fluid solver, maybe after 4 years you can only solve a very simple laminar flow, and you can't get any paper. So just use preCICE to yoink other library to get more paper. Yeah, short introduction for G+Smo. G+Smo is an IGA-based structure solver, which gives you this geometry features and also the analysis modulars. So it's basically you can from our library you can get geometry modeling and a representation for nerves, spline. We also provide complicated geometries like multi-patch. Then once you get this patch, then you can do this solid mechanic analysis in the same library. So what kind of solver do we have? We have both static and a dynamic solver. First, we can solve this nonlinear elastic deformation for 3D project. And yeah, we can also do this biological simulation. Then we also have not very good ALE fluid structure interaction solver. And you can also just throw a random equation on a very complicated geometry in our library. Yeah. So now I'm going to talk about my coupling method, which is a bit different from the existing preCICE coupling method. Yeah, so when you do the partition multiphysics coupling, first you have your structures, like in our case, we have our structure solver, and we want to couple with the fluid solver via preCICE. So from the structure, we send the surface deformation or displacement to preCICE, and preCICE map it to the fluid. The fluid just write back the pressure value to the structure. So there are two ways of coupling. The first one is you try to couple the vertex value along the interface to exchange this value. Then with this value, you lose your continuity, so which is we don't want for this essential application. The second one, if you don't want to lose continuity, you can also try to couple with quadrature point. But the problem with quadrature point is if you have a very large system, like our system, and you do some refinement, your quadrature point will increase exponentially. So it's gonna be super slow. So what do we want? First, we want a solution with higher order continuity. Second, we want to effectively communicate the information. That's why we choose this isogeometric analysis. Yeah, I feel it's a bit hard to introduce isogeometric analysis in 1 or 2 sentences. So I just steal this from my supervisor, Matthias. He had like a VR headset visualization. So yeah, on this side, this is what you can see in your real life. You can drag this control point. Then your surface can change. Yeah, so isogeometric analysis just use use this kind of nerves and spline surface to do analysis. Yeah, a little bit of mathematics. So if you want to define your IGA curve or IGA surface, the first thing you need is a knot vector. The knot vector can tell you, like basically you specify the order, the order of your curve. Then you specify the number of nodes. So in this case, you can see at the front there are 3 zeros. At the end there are 3 ones. So this means the order of your curve is 2. And here you can see this repeated knot value point A. So at this point, at point A here, the continuity of your curve is C0. Then you use this type of function and multiply it with the control points. Then you can get your B-spline curve. For the surface, you can get the surface in the similar manner. Just on each direction, you define your B-spline curve. Then you take the tensor product. Then you get this surface. So as I mentioned before, like the very important 2 components for isogeometric analysis is knot vectors and control points. And it's very clear. You can see that the number of knot vector, the number of control points here is way less than the number of quadrature points. Yeah, so that's why we derived this curve. As you can see, as the order of your curve goes up, the number of information you exchange with quadrature points grows faster than the knot vector and the control point, which is here. So we see that communicating with knots and control points yields less memory footprint. So based on that, we propose 3 ways of coupling. The first one is quadrature point coupling. This is a traditional finite element-based coupling. It's like you write your displacement on the quadrature point to the fluid solver. Then your fluid solver writes a pressure value back to the quadrature point of the solid solver. Then we also think it's also possible to communicate with fields. So we start with the solid solver. From the solid solver, we have this, instead of giving the quadrature points, we give the north vector and the control points. Every time we update our displacement value on the control point instead of the quadrature point. And from the fluid solver back, we still write the pressure value on the quadrature point of the structure solver. The final option is the pure IGA option. It's like you want to couple your IGA structure solver with an IGA fluid solver. So this one is simple. Like from the structure part, we give the north vector control point and update the displacement on the control point. Then the fluid solver also sends the north vector and the control point back, then update the pressure value on the control point. Yeah. So given the coupling method, we set up some validation case. So this is the material properties. In this case, we have this kick-off shell material, and we uniformly distributed the load on this side. Then we keep track of this U point all the time. The distributed load, we give it through a Python file. It's like a G+Smo coupled with G+Smo via preCICE. So we want to see like these 3 types of coupling can give the same result. Yeah. As you can see here, you can see these 4 lines laid on top of each other. That means our new coupling method also gives you the same result as exchanging with quadrature points. And we also test this case test our coupling cases with the nonlinear load. The nonlinear load is we add a spring load on the other side, which is a function of the displacement. For this nonlinear load case, you can also see these 4 lines laid on top of each other. So by exchanging north vector and control points, we don't lose any information. Yeah, we also have this performance evaluation. So theoretically, we should have this line, but we just calculate the exchanging time, because some people may think if we try to reconstruct a geometry all the time, we lose some. We will spend more time than just exchanging quadrature points. But if you can see this plot, our results is similar to the theoretical one, but without this part, because I think there might be some overhead time in preCICE. So our time exchange is not large enough to overcome the overhead time. For multi-patch cases, we did a small simulation as well. So for this direct coupling and IGA spline coupling, we yield the same result as well. Yeah. So after the, now I'm finished this methodology part, then how did we implement our preCICE adapter? Yeah, this preCICE adapter is a work together with Hugo Verhulst. Like first we use this black box coupling approach, which is our adapter is independent of G+Smo itself. And in our adapter, we followed this preCICE tutorial. We have initialization, data handling, mesh handling, coupling stature, and advanced finalized steps. So the implementation step is similar to the tutorial. And how can you choose your option of exchanging quadrature points and node vector and control points? Like first, you can give a metric in your script, and for the quadrature point communication option, first you can give a metric and specify the node you want along the interface. Then here you add the quadrature point mesh to your structure mesh. And how do you update your mesh? It's like you can do this evaluation of mesh deformation on the quadrature point, then send the displacement information back to preCICE. Then for our spline field communication options, like if, you initialize your geometry control points, then through the add mesh function, you add it to the preCICE, and then preCICE send it to fluid solver. Just to be sure, you add both the control point mesh and the node vector mesh. And for the information exchange, you get the false mesh back from the fluid solver. Yeah. Our adapter also try to exchange the minimum information, and we use something called a GS lookup function. Because like every time when you try to update your control points, the number of points doesn't change, and only the value change. So we get this kind of STP map to map the data value to the data location. And in principle, any value is possible, but our G+Smo is inherited. Our adapter is inherited from GS function class, so your value should also be a member of this class. Yeah, and finally, our adapter is compatible with preCICE version 3. And the main file for this adapter are GS preCICE utils and GS preCICE.h. We have to do some sketchy stuff to make our method work with preCICE. For example, we have this set mesh access region. Because our mesh is super small, it's only maybe one row or two row for the node vectors. So we want to have the mesh every time, just the entire mesh every time. So we set this bounding box to -infinity to infinity. And also because we try to map from our like parent element this node vector the node vector domain to the physical domain. So the domain dimension for our mesh and our point are inconsistent. So we insert a row of 0 to make sure they are equal. Then for these node vectors, since like for each participant, I just correct me if I'm wrong. For each participant, the number of mesh you can send is limited. So for node vector, if because the size of our node vectors are inconsistent, so we send this. So we first insert our first node, and then insert some non-values. Then at the second row, we first inserted some non-values, then the second node vectors, to make sure we have the correct, to make sure we send only one mesh to another participant. Our adapter is also being tested with our friend library, WaterLily, which is immersed boundary finite volume fluid, like fluid solver. This work is together with Mahan. From the WaterLily side, we gave the WaterLily control point mesh, and like our integration points. So WaterLily will write back the pressure value on this integration point. Yes, just the second coupling method, IGA to spline coupling method. So if you try to use our structure solver, what you, like from my side, I need to do is I initialize this mesh to you. Then I transfer my curves, node vector control points, and such through preCICE. Then you can get the point and such from your side. So this is what they do. They reconstruct the geometry and measure the displacement value. After after the first time initialization, the coupling starts. We achieved a small benchmark with WaterLily already, which is the Turek-Heron benchmark. We haven't compared our result with other fluid solver yet. For this benchmark, from our side, we only give the tail to preCICE to WaterLily, and from the WaterLily side, it can just since this part is rigid, WaterLily side will just generate this circles to the left endpoint of this beam. And the beam element, and we only use degree 2 patches, that is 4 times 4 control points. Yeah, so you can see this is our simulation result. We only compared it with the reference solution. And from the engineer point of view, it is close enough. And for this, we only run it locally in our laptop, not on the Delft Blue as such. And it's super fast, only takes like 5 or 6 minutes. Because WaterLily now has this GPU acceleration. Then the second small benchmark with WaterLily is this perpendicular flux. you can find the material there. For this, we only have a very first result. We haven't compared our result with anything. Also, we try to run this simulation together with openFOAM as well. For this, we also have we also haven't compared this result with any other solvers. Yeah, this is some work in progress. Since our ultimate goal is to have an IGA-based fluid solver, there is an ALE-based fluid solver available in G+Smo, but it's not very nice. Because for this ALE solver, when the mesh deformation becomes very large, you can't do your simulation anymore. So we developed something like a better parameterization method to allow large deformation happen. Yeah, this work is in collaboration with Ye, a postdoc in our group. So this is like the original PDE-based parameterization method. Then you can see the mesh distortion over there. And this is our improved parameterization result. You can see it's very smooth. And we also achieved this. Like if you keep your shape running for rotating for several periods, our mesh is still working. So using ALE for fluid structure interaction without mesh update, without remeshing, is possible. So in the future, we are planning to have our official release in December. Then for this one, the boundary fitted ALE solver, we are also going to release in December. And together with Ye, we are going to publish a paper on this. The next step is also like we have so many benchmarks, so many leftover works. We need to finalize this. We need to compare our results with our solver. Yeah. Okay, thanks for your attention. You can find our repository from via this link, or scan the QR code. Our work can be found under the preCICE version 3 branch. Yeah. Thanks.
A lot of interesting results. Who has questions?
Yes.
Coming from a person that mainly looks at the coupling and kind of does some amount of solver shopping, meaning that I take nice solvers and then mainly do the coupling. Mm-hmm. What time steps, what time integration options does G+Smo provide?
What kind of time integration options?
Yes.
We have this. I think for this example, we use this quasi-Newton time interpolation method.
So you're using quasi-Newton?
Yes.
And what time stepping scheme?
What do you mean? What type?
Do you use like implicit Euler, or what time integration do you use in your?
Like we choose this. We also try to use this implicit Euler scheme in our G+Smo.
Yeah.
Yeah.
Okay. Thanks.
And one thing I need to add, because this time integration scheme is fully independent of preCICE. And this work is done by another person. So every time I just use his function inside of this adapter, so I'm not too sure how he implemented this. But I can show you after the presentation.
That would be nice.
Okay.
There was a question here.
Thanks for the presentation, very interesting. My question is, are you planning to couple your solver with something like free surface flow, or given the application with interFOAM or something equivalent?
For the free surface flow, we found a library which is openFOAM. Have you ever heard this?
Not specifically.
Like openFOAM is a free surface flow library which is like developed by a professor in our group.
Okay.
Which is also IGA-based. So this is the next one we are going to try.
And if I can, another question is, what kind of measures do you plan to do with your test cases? So what you want to measure with the final application? What the final goal of this kind of simulation? Because it's very flexible, but what you want to measure? Stiffness, durability, and so on. And how do you plan to measure with your structural solver? As a long time goal, in a sense, when you go to, let's say, produce a new component of this kind of solar cells and so on.
Yes, so far, like we are only working with this small, very small and simple benchmark. What we were measuring is just like the displacement. And for this Touré-Caron example, we measure this drag and lift force. And that's it for now.
Thanks.
Yeah.
Thanks very much.
Thank you. Thank you for a very interesting presentation. You mentioned at some point that your goal is basically to move to an IGA solver for also the fluid participant.
That's my ultimate goal, but I feel it's difficult.
What is the reason? So I mean, you're using now preCICE to basically you have the freedom to choose whatever you want. So you show some showcases from openFOAM to WaterLily. But what is the added value of doing IGA for fluid? For structure, I can understand. But why would you like to have IGA on both sides?
Yeah, that's a very good question. I've also been thinking about this, because for fluid, you can't really achieve this like this IGA level of accuracy for your solver. Mm-hmm. Yes, I think for this very large scale simulation, using finite element, finite volume might still be the best option, because you have super fast, super robust simulation, and you can get like relatively good enough result. For IGA, well, sometimes it's slow, and the accuracy you improved maybe cannot compensate the difference for your solvers. Mm-hmm. But for some smaller application like how to say, the blood and the vessel simulation, because you have a very small scale simulation. Mm-hmm. Using an IGA-based fluid solver is still valuable.
Mm-hmm. Yeah. Thank you. Thank you. Mm-hmm.
So you have the G+Smo adapter here.
Yeah.
Do you also have the WaterLily coupling? Is that also on GitHub, or how can I find this?
Like this plan is actually together with WaterLily. Both of us are going to give this official release in December.
Okay, so this will be a release of G+Smo, and then you will also, and at the same time, you will release a version of WaterLily that has the adapter included?
Indeed.
Okay.
Yeah.
Mm-hmm.
And the WaterLily adapter is also independent of WaterLily.
Okay, so
Yeah.
it's a separate
Yeah.
repository.
Mhm.
Okay. Nice. I'm looking forward to it.
Thanks.
Yeah.
Another question.
Go ahead.
Thank you. Talking about WaterLily, you mentioned that it also has a support for immerse boundary method.
Yes.
Did you ever
it's
consider
Hmm?
using immerse boundary method instead of using these moving meshes or deforming meshes?
I think immerse boundary method can be more advantage in this very large deformation simulation. But with immerse boundary method, you don't have this sharp interface between your structure and your fluid. So that's why we want to explore this ALE-based fluid structure interaction to have this body-fitted fluid solver.
But do you need a sharp interface? What is the relevant, what is the, let's say, approximately the regime you are in terms of Reynolds numbers, for instance?
Because in my collaborator, Ye, he has an application with which is a rotor.
Ah, I see.
Yeah, so he needs this sharp interface.
There I can imagine you would need that.
Yeah.
Okay, thank you.
Yeah, no problem.
Yeah, I think no more questions right now. I have a list of points I want to talk to you. That's too much for now.
Okay.
Thanks for the presentation.